Hi everybody. Today we're going to continue our discussions on linear motion, but now we're going to look at linear motion in the vertical direction. So, to begin with, let's talk about throwing a ball straight up into the air and having it coming right back. Or in this example, say shooting a baseball at an initial speed of 20 meters per second straight up. So let's watch what happens. Straight up, right back down. See that again. Straight up, and just that height and time, and then right back down again. Well, that baseball, the moment it leaves the thrower's hand, or in that example, the cannon, is undergoing something called free fall. Now, what exactly does that mean? Well, an object in free fall is subject to only one acceleration. And what could that be? Well, once you're in the air with nothing in contact with you, the only thing that can affect you is gravity. Gravity is an acceleration. And the only direction that gravity can actually act is to pull you downward. That's the only way it can possibly go. So let's look at that path. Here's my ball. And initially we launched it upward with an initial velocity of 20 meters per second. If we follow its path, it went straight up some point, turned around, and came straight back down. Now, so let's look at this idea of velocity, displacements, and acceleration. Well, first of all, let's say that this is our beginning point right here, our beginning and ending point, kind of like the ground. So in terms of displacement, from the beginning up to this top point, I could say my displacement is definitely positive because it's going up the whole time. In addition, the velocity is in that direction. So I'm going to say that my velocity during that whole trip is also positive. Now, but what about my acceleration? Well, we know that when it reaches the top, it has to have a velocity of 0. Now, there's two obviously reasons. One, we saw that happen. It physically stopped for a moment. But we know one very important rule, that before you can ever change directions, you've got to stop. Okay, so in this case, before we can start going down, we had to stop going up. Now, to go from a velocity of 20 down to 0 would require a negative acceleration. Okay, well that makes sense. We're slowing down, negative acceleration. But now let's look at what happens on the second half of the trip. If we start at the top, so now the top is sort of our starting point here. And now we're on our way down. Well, now if I begin at the top, I could say I'm starting from 0. And now if that's my beginning point and down here is now my ending point, just considering that trip, I could say that my displacement is now negative. Again, considering that I'm starting here at the top and ending here at the bottom. My velocity is also negative because I'm traveling in the downward direction, in the negative direction. Now, my acceleration. Well, I started from rest and I got faster and faster. Now, you might be tempted to say your acceleration is positive, but it's actually negative. Now, why? Well, because I went from rest to a faster negative velocity. And the only way I can get faster in the negative direction is with a negative acceleration. Now, sort of one other interesting fact about this. I began at 20 meters per second upward, went to 0 under a set acceleration, something we're going to call gravity. Then I went from 0, I had the same distance I traveled, the displacement was just negative in this case. under the same acceleration? Well, and a very important concept is that the moment the ball returns to the thrower, just before it's caught, that velocity must be negative 20 meters per second. In other words, whatever you start with on the way up, you have to have the exact same velocity, but in the opposite direction, coming back down. And that's because the distance traveled in each case was the same, the acceleration in each case was the same, the idea of gravity. And what we're going to see later on is it turns out that the time is also the same. In other words, what we're going to see is that the other important concept is that the time to go up on the one side is the same as the time to come back down on the other side. So why does this work this way? It all has to do with the fact that there's one acceleration while you're in free fall, gravity. Now, gravity on the Earth is technically negative 9.81 meters per second squared. Really, that's kind of an average. Gravity varies all over the place. But for the purposes of my classes, I like to use negative 10 for two reasons. One, it's close enough in my book. And multiplying, dividing by 10 is much easier than 9.81. So for the purpose of a lot of problems that you'll see me do throughout the year, when I use gravity on Earth, I tend to use negative 10 as our acceleration. So that's what I'm going to do. Now, what does that mean? That the acceleration is never zero in free fall. Okay, never. Can never be zero in any sort of free fall motion. So when you're on the air and nothing's influencing you, you always have gravity acting on you. And gravity only acts one way, straight down. However, when you throw something straight up in the air, it must reach a velocity of zero when you reach your maximum height, because that's the point where you're going to turn around. So again, acceleration is negative zero, but velocity can be zero when you reach a maximum height, again, as you throw something straight up or down. And one other thing we're going to do to make our life a little easier is we're going to ignore the effects of air resistance. Air resistance can kind of complicate things, so for the most part in a lot of our problems we're going to pretend that air resistance doesn't exist. So, what would the graphs look like of a ball thrown straight up in the air and coming back down, or that example of the cannon shooting the ball straight up and down? Well, let's look at our three typical types of graphs that we've been doing in motion with this idea of throwing a ball initially at 20 meters per second, having go straight up and come right back down to me as a thrower. So to begin with, let's start with an acceleration time graph. So I've got my acceleration in meters per second squared and my time in seconds. Well, when it comes to this type of graph, there is one acceleration, gravity, negative 10. And it's a constant acceleration the entire time. So, wherever negative 10 would be, I would simply have a constant acceleration. And that's basically it. Okay, now, one thing is I don't really know what the time is. Okay, so I would probably really need to know what the time interval is. Well, let's look at that. If I take one of my motion equations, let's go with the easy one. Final velocity is initial velocity plus acceleration times time. Well, if I do the first half of the trip, the final velocity up at the top was 0, the initial was 20, an acceleration of negative 10. Now remember, I can never have negative time, right? That's because I subtract 20 and divide by negative 10, and that gives me 2 seconds to get to the top. Now, turns out that if it takes me 2 seconds to go to the top, it also takes me 2 seconds to go to the bottom. So really, if we want to look at the time intervals here, it would be 2 seconds and 4 seconds, because the whole trip would last 4 seconds. 2 seconds up, 2 seconds right back down, as long as I begin at this and end at the same location. Let's look at the second type of graph, which would be a velocity time graph. Now this is a little trickier. Velocity is in meters per second, time is in seconds. Let's use those same time intervals, 2 and 4 seconds. Now, my initial velocity was positive 20 meters per second. After 2 seconds, I reached the maximum height and I stopped. And then in the last 2 seconds, I went from 0 to negative 20 meters per second. So notice really this line is a constant sloped line from 20 meters per second all the way to negative 20 meters per second, crossing 0 at 2 seconds. Now, guess what the slope of that line has to be? The slope of that line has to be negative 10 meters per second squared. Because remember, the slope of a velocity time graph always gives you an acceleration, and our acceleration in free fall is always negative 10. Last graph is a displacement time graph. Okay, let's look at those same time intervals, 2 seconds and 4 seconds. Now, we'll start from the ground, call that 0. At 2 seconds, we reach our highest point, where we stop and turn around and come back to the ground. So now it's going to be a parabolic graph, okay, because there's an acceleration there. And it kind of makes sense. It looks like the path of the ball. It goes straight up, stops, comes right back down at 4 seconds. Now, of course, what is this number? What is that maximum height? Well, since we know it takes 2 seconds to get there, we could use our displacement equation. I have an initial velocity of 20. It takes me 2 seconds to get to the maximum height. An acceleration of negative 10 times 2 squared. And that gives me 20 meters of height. So that maximum height occurs at 20 meters. So that's what the graphs look like. And now this is the interesting thing. These three graphs, anytime you throw something straight up in the air and it returns to where it started, that's what those graphs always look like. The difference will be velocities and time, okay, depending on how hard you throw it and dictates how long it's going to be in the air. So let's look at an example problem and how we're going to deal with this. Here we have a ball is thrown straight up in the air at 40 meters per second. Determine the time it takes to reach its maximum height, and then determine the distance to the maximum height. So how are we going to do this? Well, what we need are some formulas. Well, turns out we can still use those exact same linear motion formulas. Now, here though, we always know the acceleration, negative 10. So you notice I've replaced the A with the letter G. G is often used as the acceleration of gravity. It's the sign for the acceleration of gravity. And basically, they're still our same three linear motion formulas. Now, here's where we have to be careful, because if I just take a quick look at this problem, it looks like I was only given one thing, 40 meters per second. So that doesn't look like it's enough information, but there's a lot of information as long as you understand the concepts of what's going on here. Now, first of all, the ball was thrown at 40 meters per second. So that must be my initial velocity. But we know it's thrown into the air. And as soon as we know that, we automatically know that acceleration, negative 10. Now, that's still not enough information. But the point is we also are told we're going to go to the maximum height. And as we saw, if I throw something to the maximum height, it has to stop before it can turn around. So I can call that point my final, and I have to come to a stop, 0. So now I want to determine time. Well, that first motion equation is always an easy one to work with when I want time. Final velocity is initial plus acceleration times time. Final is 0, initial is 40, acceleration is negative 10. Subtract 40 and divide by 10, and I get 4 seconds. So that's my time to reach the maximum height. Part B is I want to determine that maximum height, that displacement. Now there's two ways I could do it. One is to use the displacement equation. Knowing that I have an initial velocity of 20, it takes 4 seconds to get to the maximum height. I have an acceleration of -10. And that gives me 80 meters of total height. That's one way I could have done it. The other way to do it is to use my time unknown equation. Final velocity squared equals initial velocity squared plus 2ax. Final velocity is 0. The initial is 40 squared. Acceleration is -10. Looking for displacement. A little more math in this one. 40 squared is 1600. This is -20. I subtract 1600 and divide by -20, and I get positive 80 meters. And both answers should be positive because I'm going up. And that's really all there is to it. So basically, doing vertical motion free fall problems is very similar to doing linear motion problems, but this time we always know the acceleration. We don't have to go finding it, and that's a lot more convenient. Let's say you're standing on top of a building, and the building is 30 meters tall. And let's say you've taken a water balloon with you, in this case a square water balloon, which we know they all look like squares. And you see your best friend down below, just kind of hanging out. And instead of just dropping that water balloon on your friend, you decide to hum that sucker downward at 15 meters per second towards your friend. And let's assume for the sake of this problem that the entire distance is 30 meters it's going to go from how high you hold the water balloon to your friend's head. So there are probably two things your friend wants to know. First of all, how fast will that water balloon be going? In other words, what will its final velocity be as it comes into his head? And should he happen to look up, how much time does he have to get out of the way? Okay. Now, let's look at what we're given. Here's where we've got to really be careful of vectors. Now remember, all these motion things are vectors. Direction matters. So if I look at this problem, the initial velocity of the water balloon is not 15, it's -15, because it's thrown initially downward. Well, the acceleration, once it leaves your hand, once it's out of your hand, the only acceleration that can occur is gravity, -10. And the displacement, well, from the balloon down to your friend's head is a negative displacement, -30. Okay, so right away we see there's a lot of negative vectors here because everything's occurring in the downward direction. Now for part A, finding that final velocity. Well, one thing I don't see in here and I'm not looking for is time. So I run to my old friend time unknown, bf squared, bo squared, 2ax. Final squared is the initial, -15 squared, plus 2, acceleration -10, displacement of -30. If I multiply all this out, I have vf squared, 15 squared is 225, plus 2 times -10 times -30 is positive 600. So vf squared is 825. Now be careful. Sometimes people won't pay attention to their vectors, and they might end up with a negative number at this moment. You're not allowed to take the square root of a negative number. So if you ever find yourself in that situation, check your vectors. That's probably what went wrong. However, when I take the square root of 825 to get my final velocity, I end up with an answer of 28.7 meters per second. But that's not right. You see, when you take the square root of a number, the answer could be positive or negative. So now we got to remember and check our vectors. Because it's headed downward, that has to be the negative velocity for the answer. And that's very, very important. Always watch your vectors, because it's going downward, the velocity is also a negative value at the end. And that becomes very important when we go to figure out time. So now let's find that time. Well, I'm going to use my first motion equation, the easy one to use. My final velocity is negative 28.7. The initial was negative 15. Acceleration is negative 10. Now remember, you can never get negative time, right? So first thing I'm going to do is I'm going to add 15 to each side, making this negative 13.7. And then if I divide through, I don't end up with negative time. I end up with 1.37 seconds, positive. Now, if you had accidentally left this as positive 28.7, well, when you added that 15 to the other side, you would have gotten a much larger number, and you would end up dividing by negative 10, giving you negative time. So again, if you don't watch your vectors, that can really mess up what your final answer is going to be. So always watch your vectors. Let's look at one last example. Skydiver. Now, for the purpose of this one, we're going to sort of freeze the plane in midair for a moment. And we've got our skydiver who's simply going to step out of the plane, free fall to the ground, which is 2,000 meters below. But let's say when this skydiver is falling, goes to open his parachute, and it doesn't open. So then he pulls the emergency cord, and that doesn't open either. So the question is going to be, exactly how fast is he going to literally come screaming into the ground? Okay. Well, let's look at our givens. Since he just stepped out of the plane, we're going to say our initial velocity is 0. Well, free fall, acceleration is negative 10. And our displacement, he's going to drop 2,000 meters. So it's negative 2,000. Final velocity, no time. Let's go to time unknown. Vf squared equals VO squared plus 2AX. Final squared. Started from rest to negative 10, negative 2,000. Gives me a Vf squared of 40,000. Again, I can't take the square of a negative number, so the math is working out. And when I do take the square root, I end up with negative, because it's headed downward, 200 meters per second. Now, in case you're interested, that's approximately 450 miles per hour. So, what are the odds of someone's surviving a 450 mile an hour impact with the ground? And so I'm going to think, well, what if he hits water? Well, at that speed, hitting water is just as good as hitting the concrete. You're pretty much not going to survive. Yet people have actually survived this type of event. So why? It has to do with an idea of something called terminal velocity. It turns out that in real life, there is air resistance. And as you fall, air starts pressing against you more and more and more. So eventually you stop accelerating. Now, that doesn't mean you stop falling, but you stop accelerating. And so you'll end up reaching some sort of maximum velocity in free fall due to air resistance. Now, what that again means is your acceleration drops from negative 10 to 0, but you don't stop there in midair, you continue to fall. So what would the graph of this look like on a velocity time graph? Well, in this case, for terminal velocity, our person stepped out of the plane, so they started here at 0. Now they begin to accelerate at a very steady rate, but that acceleration eventually levels off to 0 at whatever that terminal velocity happens to be. Now it varies for all different shapes and sizes and things like that. For the average human, it's somewhere around 120 miles an hour, which is still pretty fast, but a little more survivable than 450 miles an hour. For other objects, it can, again, vary greatly. Some people often think that if you were to throw a penny off the top of the Empire State Building, it would actually go through a person's skull. Mythbusters actually disproved that, and one of the reasons why is because a penny reaches a very low terminal velocity in a very short time. So it's not accelerating that entire time. It only speeds up to a certain amount, and then it can't go any faster. Now, it'll hit someone's head and hurt, but they actually showed on Mythbusters that it couldn't even go anywhere through the human skull. It's just too strong. So don't believe anybody when they tell you that. Okay, so that is our lecture today on the idea of vertical motion surrounding particularly free fall. See you next time.